Hi everyone, my name is Jan Marsch. I'm a software developer from Berlin, one of the native Berliners in the room. And I want to talk about buildings in space and sun and time. That relates a bit to another dimension, to 2 or 3 dimensional maps. And that was our original topic for today. So I made this up. And this also relates a bit to my personal project, OSM Buildings. Few of you have already seen another talk today, but I try not to repeat that much, so that you see something new. But a quick intro, let's see. Please. All right. Cool. Oh. Yeah.
Can you click the pause button over there?
The what? Pause? Oh, thank you very much.
Hi. Thank you.
Yeah. So it's now a bigger topic, but I have no idea how to get.
Just press pause.
Hey, press pause. That's so now how to get there? Thank you very much. So what the project itself is about? OSM Buildings is a buildings visualization on maps, on classic web maps. It can be multiple engines. In this case, I'm using Leaflet.js engine, using some OpenStreetMaps data, but theoretically it could be Google Maps, but yeah, just need some coding. So what I'm doing is visualizing buildings on it, and it is not, like you see here, it's not a static thing, it's dynamic. So as soon as you move the map, you will also have the buildings moving along, always in correct perspective. So another specialty is that it's not requiring any special graphics card, or it's not using WebGL for rendering this. That might be a bit surprise. This one is only using 2D drawing techniques, and that's why you can easily run it on most mobile devices right now, right out of the box, without installing anything extra. That makes it fast in this mode. I don't need to repeat this. So now I'm in. Okay, I hope that's good. So what I want to talk about, buildings in space. Okay, you've already seen a bit of buildings. Adding another dimension, it could be time. I mean, my preferred choice is time, and I guess some of you have chosen time. What I want to talk about is shadow casting. I head back a bit. For example, if you see the buildings here, everything has a shadow. I hope you can see it a bit. And I want to explain a bit how that's done, and some pitfalls of it. So, and I was also asked to get a bit more into detail, to show a bit of code. So I guess everybody understands it, and it's easy for everyone.
Yes, of course.
No, that's disappointing. Very disappointing. Okay. Honestly, I've taken the formula from the web. I didn't invent this. This requires you to be an astronomist, and you have to know quite a lot of planetary things and formulas. So I can just roughly explain a bit of it, and I tried to understand this as well. So basically, what I want to do, if I want to show correct shadow casting on a map, I need to know at which time the shadow goes in which direction, how long it is, and of course this is also position dependent, where I am on Earth. So this function, which does the core calculation for this, of course takes a date, takes also latitude, longitude, position. Then I tried to sketch the thing up a bit, and also to tie the letters to the according points on the sketch. Basically, most calculations take from Earth to Sun, take the shortest path, or the shortest point, that's marked with an upper L. And then everything starts from there. So they are starting to calculate a longitude that is basically position L, longitude. So you can calculate where Earth on this path is. That's only one factor. Next factor, R, R, there's no R, that's good. That's the right ascension. Okay, it should be A. It's similar. Okay. Yeah, that tells us what the current rotation of the Earth is at a given point in time. So you also know the horizontal movement, and you also need the vertical angle that's marked with B. Of course, Earth doesn't move in that way, but we need to know at a given time what the position is. And we also always have to keep in mind that the angle of the Earth, that means the axis through North and South Pole, is different from the ecliptic. That means that's the movement plane around the Sun. So it's marked a bit here. That's the equator. So the Earth is tilted a bit. So that also comes into play. I mean, that makes it very complicated. And I guess if you already see that astronomical terms, it's hard to do. So luckily, I found a GitHub repository with all that code in there. It's more or less some code. Don't worry, at the end I have all the links which are relevant. If you want to dive into this, feel free. And that's the guy who wrote Leaflet.js, if somebody knows him. And he also attached some very good explanations. That's some Dutch site which really gets into each single term, explaining it better than I do. So let's see how we get forward. Yes. Okay. Let's assume we are successful and we have a sun position. That means at the end we have an altitude angle. Of course, that says vertically where the sun is located. And we also need that azimuth angle that shows the direction, the horizontal direction. That's basically all we need to go on with calculation. And now that's my code. In this case, if I assume something like a building, that's just a given vector. I invented a vector of size 1 just to start calculating. It doesn't need to be a building at this point. So I need to know if I would have this arrow and place the sun there, where would the shadow end? So at this angle, altitude angle, it would end somewhere around this circle. That's given after this calculation. And the other thing is the horizontal angle, that's this one. So I know from which direction it's shining. And after all, I have a resulting vector that starts at this on this tip and goes down to this. This vector, for any subsequent calculation, is always the same. So if I have a big building, maybe 3 times as high as this arrow is, then I have 3 times the size of this arrow, the shadow casting. Or if it's half the size, of course, half the size of the arrow. Is that somehow, can anybody understand this? Yeah? Okay. So really don't forget the formulas, but it's just this sketch. So a project that basically says, if I want to show my buildings at the end, every building has, of course, some points on the ground and some points on the roof line, and I want to have a proper shadow drawn on the map. That means each single point of this geometry needs to be projected. So I have it somewhere in XYZ 3D space, but I want to draw it properly on the map in 2D space, so I need a little formula to make this happen. And that's this. And this also takes, of course, into account this vector calculated before. So, I think that was really tough. I go into practice a bit. Not coding, don't worry, but quickly showing. I hope it works. So, That was great. Yes.
Green button.
The green button. Yeah. Yes, I'm using Windows too much. So, an example. So you see the TV tower here. That's a nice example. And it moves. Everything moves. Everything keeps perspective. And the shadow, of course, stays the same because I'm not moving the sun. But you also see probably a bit that each of the building points, geometry points, is also projected on the ground. So, I have a bit better example. That's the official thing, so if you open the website, you will see this. But I have a small playground called the dark side. Let's see. Okay. First looks probably the same. So I have added these nice sliders, so we can play a bit with data. Probably that makes it interesting and explains it. So, honestly, I didn't approve every formula like measuring shadow length or something. But I've seen this used in many more projects, and I think it looks like quite plausible. So, and there's also a reason to have the day of the year, or at least some dates of the year. Of course, that changes over the year, the behavior. See? So, and there should be a jump around here. Yeah, you see that jump? It's daylight saving time, also not calculated. Of course, so that also gets respected. So there should be another jump at around end of October. Yeah, here it is. So that's the fun part. Back to theory.
And we can see your algorithm. You're drawing the shadow first, and then the building.
Yes.
Because the shadow of the tower doesn't show up on the building.
Yes, that's the point. I will really come to this. You're too fast. In a bit. There's quite good reason to do this. So, how do I get back? Hang on. Where's that thing? Yes, my presentation. No. Thanks. So, that's basically one of the pitfalls you are mentioning. Doing this for each point, for each animation frame, and it's not a full 3D library, requires a lot of performance. Usually it's not doable. So I needed to do some simplifications. And one of the simplifications, as you've seen already, is just drawing this on the ground. We're skipping each building, because it's not just drawing the shadow on a building. You can't just put it on it. Each wall would have a different perspective for a shadow. And that's impossible to calculate. At least not in such a small library. If you have a bigger one, a game-like engine, you can of course do this. So that's one point I decided to simplify. So basically that's point 2. The first one, same vector for all points. Also maybe not that important, but if you have one spotlight source and you have several objects, usually if that spotlight source is close enough, you have different shadow directions. The same applies to the sun, even if it's far enough, but you have different shadow directions. Very small, but existent. I'm also skipping this. I'm giving each shadow the same direction, basically. I guess nobody really noticed that.
The error is so small, the distance of the sun is so far away that the light rays can be considered parallel.
It's almost parallel, right.
I think the rounding of the Earth has a bigger impact.
That could be. Yeah. That could be. And I've also seen some time-lapse videos where you could probably notice that a bit. I'm ignoring this, and I think it's okay. And I also introduced rendering layers. Previously, I was drawing everything on one single canvas map element, which is cool for most cases, but in this one, I split things up because the shadow doesn't need to realign to perspective. Means, if you move the map, shadow stays the same. It doesn't really change. The building itself changes. So I can save that whole rendering step. I draw it once, and as long as I move the map, everything stays the same. Only when you stop moving or when something else is loaded, then I need to repaint everything. So it saves a lot of power. And face combining, it's probably not that obvious, but if you see that schematic building on top, that has three faces, and the shadow combines everything first, and then it's drawn as one single face. That means one drawing operation, and the building itself has 3 drawing operations. So I also save some steps to that. Just a small optimization. So that was the whole performance issue. Could you imagine any other issue with this thing? Any obvious problem? Anyone? Okay, that's good. That's good. I mean, there are problems, but one of the a bit bigger problem is local time, basically. This one, like it is at the moment, just takes your viewers' local time into account. That means if you look at Berlin at noon, you have a nice shadow. If you pan over to Chicago, you won't have any shadow, but you might be surprised what's happening. Especially if I'm not showing any local time, yeah, you might be surprised. So it depends on what the user wants. So probably I need to extend this library a bit to take local time into account. I mean, that's easy. There are several services providing the time zone for each point on Earth. Just in case. So there we are. We are close to the end. So I've also put up the links. I guess the presentation will be available online, so you can look up the things and teach me astronomy. That would be good. And last one is the geonames for getting any meter information of cities. Also provide weather conditions, etc. Population. Very useful.